Thank you very much. So the purpose of this talk today is to give you some very simple modeling of supernovae light curves. Hopefully, by the end of this talk, if I will wake you at the middle of the night and tell you I'm exploding a star with this mass and that radius, with this energy, producing this amount of nickel, you will be able to tell me, okay, day 50, this is a luminosity, this is a peak. Let's go and see and look if this is correct. So this is the purpose of this talk. In order to do that, the theory should be very simplified. I will assume many assumptions which are, or approximations which are very gross, or assumptions which are not always correct. Most of what I will show you today was basically derived 40 years ago by Arnett. Some of it not. I will show where it works better, when it doesn't work so well. And at the end, if there will be time, maybe we will see how we can use these simple arguments to learn something slightly, well, not new, but not 40 years old. Most of the first part of the talk will be on the board, but I will leave this one on. So this is what I've showed at the end of my previous talk, adding what Ram was noting, that in supernovae, time is mass, except for some period at the beginning where we see a single layer of mass, which is basically the breakout layer. After some time, we see the entire ejecta. There is no more mass to probe. In the middle, time is mass, and quite quickly, roughly like t squared. And why do I put it here? Because we get into the point where we start observing supernovae over several decades in time, saying for 1 hour up to 1,000 days, or maybe even something like that. And then we need to remember, when we have many decades of time, we need to remember this was happening. All my talk, there will be a single mass. Most of my talks, there will be a single mass. Time will probe only this single mass. So this is not for this talk, but this is for you to remember. In the middle of the talk, we'll get there. We'll start probing, start looking at probing different layers inside. But at first, we'll work only with a single layer. So what we're asking is the following question. We have some mass, m. So we have a shell with mass m, which is expanding at some velocity v, and starting with some radius, which we'll call r naught, with some initial energy, which we'll call E naught. And for this, if the energy is deposited by the shock, and we'll assume it's deposited by the shock, then E naught is roughly half mv squared. And we would like to know, and we'll assume that there is an opacity, kappa, which is constant, both in time and in space. And we would like to know what is the emission coming from this sphere. So now we are calculating what I called in the last talk the cooling phase, cooling emission. So as I said, in typical supernovae, there are two sources of energy: cooling, which is energy deposited by the shock and then radiated as photons, and radioactive decay, which is an additional source which is injecting energy continuously, and this is another source of photons. So now we are concentrating only on the cooling phase, and we have this picture. Now we assume that there is only a single velocity here. Nevertheless, the width here, this d, is v times t. So we're in the homologous expansion phase. So every element r is equal to vt. Of course, if there was only a single velocity, if all this was uniform, then the width would have been constant. So we give it some delta v of the order of v, and here delta r is of the order of r. Nevertheless, we use the assumption that this single velocity is the only characteristic velocity in the system. Maybe a factor of, I don't know, of 2, 1.5, 1.2. Difference between the two, we don't care, because we'll work mostly with the scalings. Okay? And then we want to know, first question, when would be the peak of the emission? So I want time scale, and we want the luminosity, or energy scale. How much do we see? During all of this talk, I will not talk about the spectrum. We can assume thermal equilibrium, and we can use a simple formula which is a luminosity, is 4 pi sigma r squared t to the fourth, which is wrong, but not too wrong. It's a reasonable approximation. So we can take everything here. I will get luminosity and radii. We can take out of these temperatures. So let's start. First, let's ask, what is a condition? What is a point where we actually see all the emissions coming from here? So what is happening is the radiation is trapped inside because the opacity at first is high. So it's expanding with the material. It suffers some adiabatic losses. At first, radiative losses are negligible because everything is trapped, up to the point where diffusion time is comparable to the dynamical time. And then the radiation will just leak out, and we'll see everything that was trapped. So we'll see this energy minus the adiabatic losses on the way, and that's it. So we would like to find what is the time that it happens, and how much luminosity do we have. So for that, I first remind you what we derived briefly several days ago, which is what is a condition for the time scale, for the dynamical time scale, to be also the diffusion time scale. So I remind you that the diffusion time scale Td is equal to the optical depth of this shell times the width of this shell divided by c. So tau over c is the diffusion velocity, d is the width, and the time to take over the width is simply the width divided, sorry, c over tau is the diffusion velocity. So d divided by c over tau is the time it takes to get there. Now d, as we wrote over there, is vt. So we have here tau vt divided by c. Now we want diffusion time to be the dynamical time, and we get from here tau equals c over v. That's it. So let's see what is the time when we get tau equals c over v in this problem. So tau is simply kappa multiplied by m divided by 4 pi r squared. But r is vt. So it's kappa m 4 pi v squared t squared. And this is equal to c over v. So we isolate t, and we get that the time for the peak, this is the time we will see the peak of the emission. We'll verify it later, okay? So later we'll ask what happens before this time, what happens after this time, and this will not be the peak of the luminosity. It will be the peak where most of the energy is released. Okay, we'll talk about the luminosity before TP later. So TP is simply kappa multiplied by m divided by 4 pi CV square root. And I'm leaving out factors of threes and halves and all this type of factors that you can put in. Now, I will use the following notation. This board is too small. I'm used to. Let me put it here. So the notation I'm going to use is energy. I will use in units of ergs. So E51 is E divided by 10 to the 51 ergs. Mass, it will be in solar masses. So mx is m divided by x solar masses. Radii as well. Rx is r divided by x r sun. Kappa x is kappa divided by x centimeter square per gram. And I think that that's it. Oh, and Vx is V divided by 10 to the x centimeter per second. So now we can start and put and see what we get here. And what we get is 15 days if we put in one solar mass, it's 1/2, velocity of 10 to the 9, again, minus 1/2, kappa of 0.34, 1/2. That's it. So you see that if you explode one solar mass, giving it a velocity of 10 to the 9 centimeters per second, this is what we get. If we convert this V to energy, so this V is roughly square root of 2E over m, from E naught over there, we get 15 days for one solar mass to the 3/4 energy of 10 to the 51 ergs to the minus 1/4. Kappa is the same. Okay? And if instead of one solar mass is roughly what we will get for, say, type 1a, maybe 2 or 3 is what we will get for type 1b, usual type 1b. If we go to type 2, if we explode the red supergiant, this will be roughly 10. In type 1a, the kappa is slightly is different, but not too much, maybe 0.1. Then we'll get 85 days for 10 solar masses and 10 to the 51 ergs. Okay? That's it. We have the time. We explore 10 solar masses with 10 to the 51 ergs. We expect to see something on timescales of 100 days. This is roughly where most of the energy will be emitted. What will be this luminosity? So in order to know the luminosity, we need to first to know what will be the adiabatic losses. So let's do it quickly. The gas is radiation dominated. If it's radiation dominated, then the adiabatic index is 4/3. So we know that P times d P to the 4/3 equal const. We know that the total energy E is roughly P times V. I don't care about threes, and usually also I don't want only scalings. So I get that E goes like V to the minus 1 over 3. Now V, in this case, goes like R cubed or T cubed. So E is going like 1 over R or 1 over T. This is the amount of energy which is confined to this expanding sphere. Okay, so now we have all we need. And the energy radiated let's do it here. So the energy radiated is the initial energy multiplied by the adiabatic losses. Adiabatic loss is the difference between the volume at first to the volume when everything is released to the 1/3. The volume, the initial volume is R naught cube, usually R star. And the volume at late time is simply VT cube, R. So this is going like R naught over R, which is equal to E naught R naught over VT, which is equal roughly, well, all these equals are are roughly. We'll put, if instead of E naught, half MEV square, MV square, sorry. So this is not MEV. So this is half MV square R naught divided by VT. So I can take this out and let's stop here. Okay. So said, let's take from here, m v r naught divided by 2t. Now, what would be the luminosity if this is the energy released? Any suggestion? I have to divide it by something with units of time. What? Tp. I'm releasing this energy over a time scale, which is Tp. So L is ER divided by Tp. Yeah. The energy, so no, I'm not talking about the energy. So E inside what I'm counting here is the energy which is not released. I'm doing the following assumption, the following approximation. I assume that everything is confined. I keep everything inside up to time Tp. And then at Tp, I said, OK, go. So E is the energy of the radiation, not the total energy. Total energy is conserved. Actually, very quickly, you have the shock. The shock goes through, half to radiation, half to kinetic energy. And then the half that you gave to the radiation, after the radius double, everything goes to the kinetic motion. And from this point on, the velocity is constant. So I can get it, the velocity is constant. The radius is much larger than the initial radius. I get to what I call the homologous phase, not what I call, what is called the homologous phase. And then I just keep tracking of how the radiation energy is going to be degraded by adiabatic losses. That's it. Here, yeah. So I'm releasing this. This is OK for every time. This is L peak. So it's ER at the time of the peak divided by T peak.
I think the confusion really was that your ER there is the total energy and radiation.
Yes.
That's the sub R.
Yes.
Some are hearing released, but the sub R is for energy and radiation.
Yes.
Okay.
OK, this was a OK. Yes.
Shouldn't everything be confined up to TD, to the breakout, instead of TP?
No. At the breakout, only a very narrow shell is releasing its energy. Very, very narrow. Everything, and how narrow? 10 to the minus 3 solar masses, 10 to the minus 6, 10 to the minus 9, depending on what is the radius of your star. All the rest, all the 1, 5, 10 solar masses, keeping the radiation close. It need to expand by several orders of magnitude before it's releasing the energy. And during all this time, as long as the diffusion time is much longer than the dynamical time, effectively the radiation in the gas is a single fluid, and it's cooling adiabatically, and you can just use usual hydrodynamics to follow the internal energy, which is basically the radiative energy. Okay?
When you said the first time you do for every R, this is true for every R up to
this point.
Up to this point.
Yes. So now we just take this and divide by that, and we get mv r naught divided by 2 Tp square. Tp is over there. T at the peak. So this is 4 pi Cv divided by 2 kappa m times m v r naught. And you see a nice thing. The mass goes out. Actually, we don't care for the luminosity about the mass. We do care about the velocity, which together with the energy is related to the mass. But if we know the velocity, then we don't care about the mass or the energy. They are not coming separately. And so altogether, we have 2 pi C V square divided by kappa V square R naught. And if we put the numbers, then we get 10 to the 41 erg per second for velocity of 10 to the 9 radius square, radius of 5 solar radii, and kappa of 0.34. This is roughly what you will get if you explode, say, a Wolf Rayet. If you explode a red supergiant, So the velocity here is usually lower, say 3 times lower. So you get about 10 to the 42 erg per second, V 8.5 square, R 500 divided by kappa 0.34. And if you want to take out the velocity and use the energy and the mass instead, then you get this again 10 to the 42 erg per second for an energy of 10 to the 51 erg, a radius of 500 solar radii, and 10 solar masses. Any question? Because I'm basically done. Sorry. More questions? Okay. So next, let's ask what happens before this peak and what happens after this peak. Okay, so we'll try to understand what is going before and what is going after. And let's start with what is going before. Oh, just one more thing I want to show you. It's not peak of the luminosity. It's not the peak of the luminosity. It's the time over which all the energy is released. So it's E-peak, actually. I will show that the luminosity is actually going down before that. Okay, so this is what I'm going to show now. It's not really the peak of the luminosity, but this is the typical time scale over which you release most of your energy.
Luminosity is higher before, but it goes
like
down
slower than
to the -1, then it's still after that.
exactly. So the luminosity is going much slower than t to the -1. In the approximation we'll make here, we'll see it's constant. In this approximation, which is wrong. Okay, just one more question we can ask. What is the ratio between the energy radiated and the initial energy of the system? So we can see, so it's E radiated over E naught, and this is the energy released at the end, not the energy in the radiation at every given time, the energy released at the end. And we can see that this is R naught divided by V Tp. And this is equal to 0.01 M10 to the minus half V9 of V8.5 to the minus half kappa 0.34 to the minus half R500. And if we put it with energies, then it's, again, 1% the mass to the minus M10 to the minus 1 over 4 energy, 51 ergs to, again, minus 1/4 kappa 0.34 to the minus 1/4 R500. So this tells you that, for example, if we explode a red supergiant, we expect roughly 1% of the energy to go out as radiation. Okay, you see the dependence on the energy and the mass is rather weak. The dependency on the radius is very important. It's Well, it's linear, stronger than anything else. And for a red supergiant, we'll get 1%. For a blue supergiant, we'll get 0.1%. For a Wolf-Rayet, we'll get 10 to the minus 4. And indeed, if we look at type 2Ps, roughly the energy release is 10 to the 49 ergs. 10 to the 51 ergs explosion, 10 to the 49 ergs. This is roughly what we see. The rest, 10 to the 51, we actually don't see at all. Unless there is interaction. If there is interaction at some large radius, we can convert the kinetic energy to internal energy, and that's it. Now, the dependence on the radius is linear for a very simple reason. The radius where the radiation is released is independent of the initial radius. So you see, all we care about is the mass and the velocity, or the mass and the energy. We need the mass and the energy to know where the energy is released. You see? Here, this time scale, and this time scale times the velocity is the radius, independent of the initial radius. Obviously, why should the radius where the radiation is released care about the initial radius? How much energy goes to adiabatic losses depends strongly on the initial radius. So if you start very large, the change in the volume between the point where you start and the point where the radiation is released is small. So adiabatic losses are not so severe. If you start very compact, it's huge. If you start with a wide dwarf, nothing left. You will release 10 to the minus 6. Maybe 10 to the 45 ergs will be released in the form of cooling emission. Okay? The initial radius of the explosion, which is typically the initial radius of the star, radius of the star, is 500 solar radii. 3.5 10 to the 13 centimeters.
Okay, but the initial, not
The initial. This is why it's capital R with the 500. Yeah. Okay. So now let's ask what happens before this time, and there are two ways to do that. To make this calculation in a very simple way, I will use one, which is not everything I've shown you now. This is what our net presented. I will show you a way to do it which is different. Later we'll do something similar to that, using the same assumption that our net did, and we'll see what is the difference, where they are the same. So now, when we're asking about what we are going to see before that, we are going to do the following assumption. We'll say we have our shell. I'm plotting it here as not spherical, but it's unimportant. And in this shell, we can divide this shell to two regions. And the difference between these two regions, and you know that, of course, if this is the observer, that if I go from here, the optical depth increase as I go in. So if I start here, if photons start here, it's diffusing to the observer very quickly. Photon from here will take slightly more time. Photon from here will actually start diffusing on the other direction. So I can find here a location. This is where T is equal to diffusion time. Or, as we have shown, this is where tau is equal to C over V. And said everything that I had here to begin with went to the observer. Everything that we had here is fully trapped. Of course, diffusion has some weights, and I ignore all that. I put a sharp location. Everything from here went to the observer. Everything here remained trapped. So in this approximation, what will happen with time? With time, this location is going backward, because everything expanding. T is going up. Tau is going down. So if tau is going down, it's enough. V is constant. Tau goes down. So we go farther in. Tau of the entire system goes down. So the location where tau equals C over V goes in. So let's assume that this is a time t. This is some time t plus delta t. So what will be my luminosity? Where is the energy which is released to the observer over the time delta t? This, what I have here. Everything that was here already went to the observer. Okay? Whatever I have here is still trapped. This part is what's going to the observer over this time, delta t. So let's call this region delta m. This is the mass locked here. And delta E is the energy locked here at the time that we release it. And we'll introduce a coordinate, which is a mass measured from outside in. Okay, so we will use a coordinate m, lowercase m. So m here is 0. M here is m star. And this is just one dimension. It's a Lagrangian coordinate going from outside in.
Okay.
Yes.
I think the way you explained it was a little bit confusing.
Okay. So can you explain it better?
If I may, yes. Like in approximation where the velocity is homologous, like when we go away from the observer, the velocity goes down. So we are always looking at the time where the dynamic output time is equal to CO2 to the diffusion time. So when time increasing, the diffusion time is increasing.
No. What is assuming a constant velocity. What is important here is not the velocity, it's the radius. When the radius is going up, let's look at this location. This location for a given velocity, the opacity, the optical depth here goes like 1 over r squared. So if here tau is, if at some time tau equals c over v is here, at later time it will be here. Because tau is going down here. So it's now not equal c over v anymore. Here it's also going down. Here it does equal c over v after delta t. So the
velocity there is lower.
no, I assume that the velocity is constant. I approximate it as if the velocity is constant. I neglect the dependence on the velocity. A part for the story is that everything expands. That's it. It, of course, will introduce some errors. But because the velocity is not the main player here, this will be small errors. Okay. So let's look here. Okay, so now I will write what is tau of m, the optical depth of the mass coordinate m as a function of time. So tau m is simply kappa multiplied by m. Now this is lowercase m divided by 4 pi r squared, which is kappa m divided by 4 pi v squared t squared. Now t is just time, is a variable changing. And this is equal to c over v. This will tell me exactly what is the location here, how far I'm in. So m of t, this is mass exposed at time t is 4 pi cv divided by kappa t squared. This is what I told you, that when we look in with time, we probe deeper and deeper, roughly as t squared. This is t squared. Okay? So what is delta E that we have here? Delta E is the initial energy that was here. So at first, when there was an explosion, what is the amount of internal energy for radiation and radiative energy, radiation energy that was in this layer? We'll call this delta E naught. E naught is what deposited at first. And I multiply it by the adiabatic losses. So everything, all the mass suffer from the same adiabatic losses. R naught divided by Vt. So also this chunk of mass suffer these losses. And this is because this chunk of energy was locked, trapped in the gas all the way up to here. So it's just part of the gas and it suffers adiabatic losses. So, and this dA naught is roughly delta M V squared R naught divided by Vt. So it's delta M V R naught over T. Now the luminosity is simply the E to dt. So it's V R naught divided by T dm to dt. Simply that. Now m goes like t squared, so the m to dt goes like t. This is proportional to go like t squared, dm to dt. I will write it here. dm to dt goes like v times t. So I get that this is going like v squared times t. Sorry. Like v squared times r naught. And in our approximation, both are constant. So in this approximation, before what we call the peak luminosity, the luminosity is constant. So it's not really the peak luminosity, it's the peak of the energy. Now, if I introduce some gradient to the velocity, you see from here that when I go inside, what happens to the velocity in real case? I remind you that we're in the homologous expansion, so r equals vt. So smaller r, smaller v. So in the real story, when we go in, v goes down. But by how much? At most a factor of 2. Usually, over the time that we probe. Maybe a factor of 4. The radius can change by orders of magnitude over the time that we probe. So altogether, what we'll have is a luminosity it goes like that. So what we got here is something which is constant up to Tp. And this height here is depending mostly on the radius, on the initial radius, also somewhat on the explosion energy, the initial mass. In reality, it will go very slowly. How slow? Actually, we already solved for that. So now I'm doing the simple stuff. Last week I did the complicated one. So if you will go back to the slides that I showed after the shock breakout, actually, this is exactly what we solved after the shock breakout, when it's in a spherical phase. And this depends somewhat on the structure of the envelope, but roughly it will be like t to the minus 0.3, more or less. Okay. Now let's ask what happens after this point. So let's see what happens to the velocity after T peak. For that, we'll use a different approach, which is actually the approach that Ahmed did. We'll do the following. We'll write the following equation. Assume. What I said to the velocity? The velocity is doing nothing. It's continuing the same way. No, let's see what happened to the luminosity. So let's.
Can you remind me this minus 0.3?
How do I get there?
Yeah.
I had half a talk about that.
On what does it depend?
It depends on several things. It depends on the velocity gradient, or two things. It depends on the velocity gradient. So what is v as a function of m, or m as a function of v, but not only that.
It's the density profile and this
It's just the density profile. Just the density profile. But from the density profile, you should take two things. One is m as a function of v. This will be probably, this will give you more than halfway. The second thing that you need to realize that each mass element here, where I just erased it, had a different initial volume. So when I go in, the adiabatic losses are not the same all the way. So I need also to know, to take into account what was the width of the initial shell that now is delta E. So if I account for both, for the dependence of the velocity on the mass, or mass on velocity, and the dependence of on the, and take into account the proper adiabatic losses, then I get that. Okay. So let's try to calculate the following thing. Let's ask how much energy, in radiation of course, is confined to the expanding sphere. Say below tau equal 1. It's a good place to be. Okay, how much energy is confined to this region? Now, at first let's assume there are no radiative losses and no nothing. In this case, no losses and no gain. I hope I'm writing losses correctly. dE to dt, what is it? I remind you that E is proportional to 1 over T. So this is simply minus E divided by T. What happens if I add radiative losses? So let's assume that at any given time, we have some luminosity, radiative luminosity, from this sphere. How does it change the equation? dE to dt is equal minus E divided by T minus L. That's it. L is how much energy per unit of time is lost from the system. So now this is my equation. All I need to do, if I know how to quantify L, then I can solve that. Now, of course, I can use it. I can use it to solve also the early part, what I just did. We'll do it later. We'll show what happens when we do that later. But now let's write it. Well, let's find what is L and solve what happens at T, which is much larger than this Tp. So how can I estimate what is L roughly? What is the mechanism over which radiation is radiated? Diffusion. This is the only mechanism we have here. Okay, so it's diffusion. How long let's assume that we freeze everything. We have some energy inside the sphere. How long it will take this energy to leak out, roughly? You remember we defined the diffusion time? This is the time over which the diffusion, the energy is leaking out of this ball. So the luminosity at any given time is roughly the energy that we calculate here divided by the diffusion time. Now the diffusion time, I remind you, is tau d over c, which is kappa m divided by 4 pi v square t square multiplied by vt divided by c, tau d over c. So if we can write this, so we take all that. This is Tp. This is what we call the peak time. So what we have here basically is T peak time T peak divided by T. So I can rewrite this equation. It's roughly minus E divided by T minus E times T peak square, times T divided by T peak square. Yes.
And this is T peak square without the T, without this T.
So good that you keep track of what I'm doing. Good. So I know that at least you are with me.
I will never leave you.
Yeah, we already checked that. Anyway, so now in this equation, when we go to T peak much larger than T, which one of these is larger? Well, obviously that. T peak is much larger than T, so this is a dominating factor. So we can write this roughly as minus E divided by T peak square times T. So this is the equation. The e to dt is roughly E times T divided by Tp square. This equation is easy to solve. And what we get
This is late time. At late time.
at late time, this is what I go here is T much larger than T peak. So what we get is the energy at T much larger than T peak is roughly E at the peak when it drops exponentially, even super exponentially. T square divided by 2 T peak square. And the luminosity is E, the luminosity at T much larger than T peak. Is roughly the energy at this time divided by T. By T diffusion, sorry, not by T. Because T diffusion is the time over which we drain all this energy. And this is roughly L peak times T divided by T peak e to the minus 2 square divided by. So now we can continue. Looks like that. Now in reality, we almost never see that. Because usually when we see cooling emission, we don't see it. Actually, something happens, which is usually in type 2 peak supernovae. Something happens before we get to these T peaks that we measure here that makes our calculation inaccurate to the point where it's not really very useful. And we'll get to it in a second.
This equation over there has an analytical solution for both these large and small together combined.
Yes, and what happens when we go to the small one? Exactly what we got here. But, yeah, I was going to go to there later. But we're getting exactly the same solution, but with a very different approximation. When we go to short times, we make the approximation that the ejecta is divided to 2 separate regions. One, everything is going out. The other, everything is kept unchanged. Here what we are doing, we're averaging what we have inside over the entire region. So we assume that everything is drained together. We have a single zone which is uniform. Now we get exactly the same solution because in the previous assumption that we did, we assumed that it started from something uniform. And then it was uniform at first, and then we got, and the way that this went in is exactly equal to the time over which this is draining out, and we're getting exactly the same solution. But if what we had at first was not uniform, we could use the previous method, which is dividing to 2 regions, and then just follow these regions with the non-uniformity in them, but we cannot use this one. Because this inherently assumes uniformity. So this constant I can get both ways. This part I cannot get with this formalism at all. I will never be able, at least maybe someone can. I do not see how I can use this formalism and get what happens before T peak to the next level At the zeroth level approximation of uniformity, it can be uniform in initial conditions or uniform at every time. It will be the same. Okay, this is what I said. We can use this to calculate the early time, but we cannot use this to go to the next level and improve and get actually something which is better. Okay, anything else before we go to the slides? No. E is the energy in the which is locked in. T is now much larger than T diffusion. Much larger. Now we're in the regime where it's much larger. Okay, T is 1 year, T diffusion is 1 second. E is the energy here. How long it will take this energy to leak out to the observer? 1 year or 1 second? 1 second. 1 second. Okay, if the diffusion time is 1 second, the dynamical time is 1 year. E is the energy in this sphere. The time it takes the energy to leak out now, it's just the diffusion time. It doesn't care how long, past, since, whatever. You have chunk of gas, radiation inside. It diffuses over the diffusive time. So the energy E is leaking. Say half of this energy goes out over a diffusion time. So the luminosity is E divided by T diffusion, not E divided by T. Okay? Before I got here, the diffusion time was the dynamical time. This was my equation. So I can switch between the two. I just needed to find out what is this relevant E, which was at first depending on where I am in. Now E doesn't depend on where I am in, actually depends on how much was lost. This is why it's exponential. On every diffusion time, it's losing half of its energy. It's super exponential because of every diffusion time becomes shorter. On every dynamical time, sorry. The diffusion time becomes shorter. So it's becoming super exponential. Okay? So let's switch now. So first, let's see how this approximation that we did, this very simple theory that we did, compares to observations, and then we'll see what happened when we add nickel into the game. So cooling emission. Here you see an example. This is a type 2p supernovae. Let's look at the luminosity. Roughly okay. This is a red supergiant that exploded. Roughly okay. Look at the time. Roughly okay. That's it. We are good. We got the luminosity and the time correctly with a very simple arguments. Now, we see that the luminosity goes slowly down with time, which is roughly what we expected. But is it really what we expected? Can someone tell me what is the power law here? It's a bit difficult. Why? Because we are used to look at supernovae in linear, semi-log, and not log-log. One thing that I would like you to take home is that now that we start having observations on scales of hours today after the explosion, and you can follow them for at least 100 days, which is a duration over which we see something, it's much more illustrative, much more indicative to look at log-log and not semi-log. Because I told you supernovae are logarithmic beasts. If we see 1 decade in time, I don't care. You can look at it everywhere you want. If we see several decades in time, we have information about several decades in time, look at it in log-log. Now, tell me, is it what we expected or not? Look, well, obviously it starts well. This is okay, this is fine, we're happy. This is not t to the minus 0.3, it's maybe it's roughly t to the minus 0.5. Maybe the structure of the envelope was different, maybe our best theory is not so good. But something happens here. See, something here is fishy. Maybe something else is coming in, I don't know. let's look what happens to the temperature. If we do everything that we did here, and we calculate the temperature simply by taking the luminosity and divide it by the radius square, and the radius is simply Vt, we'll see that also the temperature goes like a power law, and it roughly goes like T to the minus 0.5. This is what I told you. Believe me. Okay, at early time, temperature starts at 16,000 Kelvin, goes down. This is roughly 0.5. We are happy. But over here, somewhere about 30 days, which is also roughly here, 30 days, you see something happens to the temperature as well, not only to the luminosity. Now I look and I see this is happening somewhere around 7,000 Kelvin. Any suggestion what may happen here? We already heard 7,000 Kelvin today. And this is the ionization, this is the point where hydrogen recombine. So everything I did so far was assuming that kappa is constant. Okay? Even if there are modest changes with kappa in time, I can still work with that. But once I get to the point where kappa is changing, is very sensitive to the temperature, how sensitive? Like that. So here you see, this is for different velocities, for different densities, how kappa changes with time. How kappa changes with temperature. You see it's roughly constant up to here, only almost 100% ionized. Here there is a small bump related to the bound-free and free-free opacities, which are playing some role, negligible role, at higher densities. Typical densities that we have in red supergiant are more towards the 10 to the minus 13. But what the most prominent feature here is factor of 2 in the temperature, factor of almost 4 in the optical depth, in the opacity. And this is just due to the fact that electrons recombine, the atoms recombine. I don't have any more free electrons. The opacity is still dominated by Thomson opacity. So that's it. Now, if there was nothing else, it would go on and go to 0. Here, molecules start to give opacity, to form. And around 3,000 degrees, it levels up again. So between 7,000 and 3,000 degrees, we have this recombination. I will not go into this recombination. I will not. I will just show the following. This is from Dane's paper. What the recombination doing in 3 sentences. What happens is that once the temperature at the photosphere, where tau equal 1, get to about 7,000 degrees, everything out is recombined. And the point where tau equal 1 start to recombine, then the optical depth, let's say at tau equal 2, is dropping very quickly. Now, the energy density, and this is what I don't have time to show you, grows as we go in with tau. It's related to what Lars was showing, exactly the same thing. As we go in, the luminosity is constant. Tau equal 1, tau equal 2, all the way to tau equal c over v, the luminosity is constant. But the energy density of photons, of the energy density goes up simply because the diffusion velocity is becoming faster as we go towards the photosphere. Remind you the velocity of diffusion is tau over c. Where tau is 1, the diffusion velocity is c. Photons just run freely. So the energy density is related, of course, to the temperature. So tau equal 1 goes down, recombines. So tau equal 2 now don't have anything in front of it. The energy density goes down, so the temperature goes also to recombination temperature, and it goes down, and tau equals 3 and 4 and 5 and 6. And we start having a recombination wave, which is going very quickly, because the energy behind this optical depth cannot be supported anymore. And this is what you see here. So this is the hydrogen ionization level as a function of velocity. Velocity is mass. Okay, everything is homologous. Velocity is mass. And you see, and this is different curve at different times. And you see how sharp is recombination with the ionization level, how sharp, how thin is the layer over which we have this recombination. And tau equal 1 will always be somewhere here in this layer. So the photosphere and also the temperature at which we observe it will be on somewhere on this layer, and this is going out very rapidly. So ionization is serving, because ionization, again, by the way, this is related. Remember that I talked with you about the creation of pairs which is an exponential process, and therefore serving as a thermostat for the temperature behind relativistic shocks? I said that. This is the same thing here. Ionization is an exponential process because ionization is done by the wind tail of the spectrum. We change the velocity as a temperature. So remember, ionization energy is 13.6 eV. The temperature here is below 1 eV. So small change in the temperature, huge change in the ionization, and this again serves as a thermostat. And this sets the temperature to be roughly around 7, right here, it's level off. So the temperature is now constant. The optical depth is running in faster. What happens if the optical depth is running in faster than before? I'm releasing radiation more efficiently. Hence, it's brighter than what I expect. Of course, it will be shorter than my T peak before. The fact that the recombination kicks in, it will be shorter, but not much shorter. Why? Just because recombination kicked in after 30 days, while my typical time was about 85 or 100 days. So to an order of magnitude, ignoring recombination is not too bad. If we actually want, and usually in all supernovae, this is what we usually see. This part we don't see in many of them. So if this is only what we see, then recombination is everything. And we need to understand it properly to understand exactly what are the features that we observe. At earlier time, recombination is not really important. And it happens to be, it's not necessarily, it happens to be the same. Roughly the same time where recombination kicks in and where we approach the time where radiation would be released by diffusion alone without recombination at all. So I have 15 minutes. Let's talk about radioactive heating. So if we take about 0.1 solar mass of nickel and we let it decay, this is the heating rate that we get. Over a half time of 6.1 day, tau of about 8.8 days. Tau is what we have in the exponent. Nickel is decaying to cobalt. And later, over about 100 days, it's decaying, cobalt decays to iron. And you see that we get at first for 0.1 solar masses about 10 to the 43 ergs per second. On a time scale of about 100 days, we get somewhere around 10 to the 42 ergs per second. This is for a 0.1 solar mass. So now we have an additional source of energy that goes into our system. This is again in log-log. If we go to the nice semi-log, which is usually the way that figures are plotted, this is how it looks like. And you see that in the semi-log what is nice, and that here we have a linear curve. And if we count it in magnitudes, so this is roughly 1 magnitude per 100 days. The energy injection goes down by 1 magnitude, not 1 order of magnitude, 1 magnitude, observable magnitude, in 100 days. Now, let's look at our supernovae before, and let's choose to, I don't remember how much here, about 0.001, no, about 0.01 solar masses of nickel, and let's plot. Do you see anything which is suggesting that we have some nickel in this system? Okay, so the tail here is exactly following the injection rate of nickel. Why is it? What happens here? So here we had, this is even this decay here is even faster than our super exponential before. But after we had this, and after, if we had only cooling emission, this should go down very quickly. Now something is kicking in here. What does it tell us? That in this type 2p supernova we had what? We had nickel. And this nickel contributes to the emission. Now it contributes to the emission also here. But here the cooling emission was much brighter than the nickel. Now, at this point, diffusion time is much shorter than the dynamical time. So this implies that every atom of nickel which is injecting energy into the system, this energy is immediately radiated away. So no energy is kept over a dynamical time. In our system, whatever we inject in goes out. We inject nickel, we see the decay of nickel. Okay. So in every type 2p, which is basically cooling emission up to some point, after the plateau, we go from the photospheric phase to the nebular phase, and the nebular phase is dominated by nickel. What happens in other types of supernovae, all the type 1s, and also some case type 2, the 87 like. Here we see all these supernovae are powered by nickel, not by cooling emission. We'll see in a second why, but all these are powered by nickel. If they are powered by nickel, then we have here some rising phase. We'll talk about it shortly. But at this side, you see, we expect to see the nickel exactly like in the type 2p. And indeed, in 87A, it is exactly like 2p. In type 1, it's not like 2p. It's not exactly like that. I will say a few words about it later. But this is a point where the diffusion time is becoming shorter than the dynamical time. So we just see exactly what is injected into the system is going out immediately. All this part here, and here, and here, the diffusion time is longer than the dynamical time, and therefore the energy injected is accumulated and suffering from adiabatic losses. So we need to account for that. Now, I would just say that once we get to type 1s, and especially type 1As, and then we'll talk about it, the approximation of a constant kappa is not trivial at all. Unlike ionized hydrogen, where we can assume that kappa is constant, once we start dominated by lines, this is a completely different story. And from some reasons that I'm not fully understand, maybe you do, kappa of 0.1, for example, is a good approximation for the opacity that irons give you. You can just use kappa of 0.1 and calculate everything, 0.1 centimeter square per gram, calculate everything as if it's a gray opacity and constant, and it's not good. But it's not increasingly bad, it's amazingly bad. Okay, all those kappa is certainly depending on the very strong dependence on the frequency, much larger at higher frequencies, much lower at lower frequencies. And it's also not uniform in space and not in time. It provides a reasonable approximation. So now we can use exactly the same equation as before. We just need to add this injection of nickel. So we have this equation. L is again energy divided by diffusion time, and TD is the same as we calculated before. So we can just integrate it. 5 minutes with your favorite software, and this is what you get. This is what you get for an injected for a mass of 1.4 solar masses, 0.7 solar mass of nickel, 10 to the 51 erg of explosion, and kappa is 0.1. Okay. Now you see that the time scale, 15 days, the luminosity, 10 to the 43 ergs. If we look at type 1s, around 10 to the 43 ergs, explosion was somewhere here, 15 days. So you see that this very simple approximation gives us rather accurately factor of, say, a few, the peak time and the peak luminosity. And also you see that in this specific case, if I want to know how much nickel I have, and we'll see later that this phase is not so good to measure nickel, we can just use the point where the peak is, assume that this peak is equal to the release by nickel, and we get the nickel in mass. But this is a coincidence. It's actually a coincidence that works reasonably well for type 1s, for type 1As. If we will try to apply it, for example, to 87A, not so good. Not so good. Okay? So this is an approximation that's often used. It's not too bad. When you actually calculate 1As properly, it turns out to be reasonable. But it's not a general feature of nickel-powered supernovae.
You wanted to point to the peak, right? No, not this one before.
Well, it depends what you want. If you go to the peak here, and you assume that the nickel at this time, then you will get this amount of nickel, which is larger by a factor of about 3.
So before you pointed to the crossover, you cannot know what the crossover is.
No, you don't know what this crossover is. Yeah, for some reason, they don't come with that. No, actually, they come with this, so I can continue. Now, we can do an alternative model. We can do the following. We can use exactly the same model, that we used before to calculate the emission from the cooling emission, separating the two regions. One region where everything is going out, one region where everything is kept in, and calculate what is the luminosity. So then we say the following. The amount of nickel that we see, so what we see at every given time is a nickel deposited, sorry, the energy rate deposited by nickel in the region that we observe. So there is one observer where everything we deposit goes out, and one region where nothing goes out. It's exactly like before. We have all the part which is up to the diffusion length, and all the part which is to the diffusion time. The diffusion time is smaller than the dynamical time. All this region is radiated away. Where diffusion time is larger than dynamical time, all this region is kept in. So this is a mass over that satisfies tau equals C over V, just like before. This is M of T of before. Of course, we take the minimum between that and M ejecta. Once we see everything, we see everything. We cannot see more. And we multiply it by the fraction of how much of our mass. We assume a uniform fraction. How much is in nickel? And then that's it. L is simply the nickel mass which we see multiplied by the nickel deposition, the energy deposited by nickel per unit of mass. This is what we get. And now I plot it again in log, because I'm interested mostly at what's happening at early time. So at very late time, I see all the mass, I see the deposition rate, of course, they are the same. You can see that also at early time, they are exactly the same. The approximation is similar. The difference here is because this is accounting for some adiabatic losses, so it's giving you some coefficients. Here there are no adiabatic losses, but they are basically the same, and both are going like t squared. Here near the peak, actually, if you want to do something which is reasonable around the peak, use the former formalism, not the one that I showed you here. But what about this part? Here they are the same. Do we really expect the luminosity to increase like t squared at early time? What is the main assumption that we did here? We did here a very strong assumption which is practically wrong. We assume that this fraction of nickel is constant all along the star. Then just showed you. We have a lot of nickel inside and not so much nickel outside. So at very early time, this fraction of nickel, how much nickel I have in the exposed mass, is depending much more on what is the fraction of nickel in the outer layers than on how much mass I see. If I have no nickel at all, I don't care how much mass I can see. I don't see anything. So actually, if you want to improve on that, using the other mechanism is much better. All we do is we use exactly the same thing. We just plug in what is a function of nickel, what is a fraction of nickel as a function of mass coordinate as we go in. This immediately will give us a much better approximation. Also, this approximation is not great. It's not correct, but it's better than the previous. Okay? Now, there was about several years ago, there was a practice that people looked at very early time and tried to find out what is the explosion time. And they said, okay, we don't know the explosion time, but we see this part. We see here maybe 2, 3 points, maybe 1. And we can fit this 1 point to a t square and go back. No, I'm joking. Usually we have excellent measurements over here. Still, if we don't know what is the explosion time, we can fit almost any power law we want. And then you go back and you find you say exactly the explosion time plus minus whatever is your fit, how many points you have. Usually it will not give you the right result unless nickel is uniformly distributed all the way to the edge. What you actually expect is that in the outer layers you don't have nickel. So you expect to have something which is called a dark phase. It can be 1 hour, it can be 1 day. It depends where, as you go in, your nickel is waiting. Okay? And only once you start seeing regions where there is nickel, it starts rising. Okay, now you have to include the fact that the opacity depends on the luminosity because ionization depends on the luminosity, and it's becoming much more complicated. And also the separation of regions that you see and regions that you do not see is not so good. Because if I have huge amount of nickel here and no nickel here, then the luminosity will not come from this no nickel here, it will come from diffusion tail, something which is diffusing from here. Although the diffusion time is larger than dynamical, something is diffusing out, but we'll not go there. But if we go to very early time, then the model I showed you is not so good, we need to improve. What happens if we go to late time? Actually, it doesn't work as well. At least not in type 1As. This is what you expect. This is 1 magnitude per 100 days. This is what we observe. Okay? So it again. It's different, but why? I just explained so nicely why it should be, why it's not.
You wrote the answer, so.
Yeah, I wrote the answer. So what is it? Okay, so not all the energy deposited by the nickel is actually going to thermal radiation, because we need to thermalize the gamma rays. The opacity of the gamma rays is low because they are in the MEV range, so Klein-Nishina loss suppression of the cross section, and it's actually lower than the cross section of the for radiation. And of course, as this is becoming optically thin, so gamma rays just escape. This is the way that we saw gamma rays. So you have seen before that we actually measure the gamma rays in the nebular phase. It's because they are escaping. But if they are escaping, they are not going into heat. They are not going into heat. We do not see it in the thermal bands or any bands that we can measure. So this is why this phase is not so good. So what I've showed you is how we can use this beautiful theory to estimate roughly what will be the peak and where it will be, but nothing more. It cannot be trusted before, it cannot be trusted after. Okay. I just want to remind you one thing. When we look in the optical, okay, what we actually see, for example, this is type 2p, so the luminosity is doing Z. But the optical is going up. And this is because when we look at a single band, we don't see the bolometric luminosity, unfortunately. It would be much easier to model if we would have. And the temperature is going down. So this rise is because the temperature is going down. And the luminosity in the optical, once it's on the Rayleigh jeans, goes like the luminosity divided by T cube. So if T cube is going down faster than the luminosity, we have a rising light curve, and this is what happened in type 2Ps. When we look in the optical, it's actually going up. And the peak here is related to the time where the luminosity, or the temperature, gets roughly to the windows that we observe. At this point, we are not in the Rayleigh jeans anymore. Luminosity goes down, but the temperature doesn't play a significant role, and it starts going down. So this peak is actually unrelated to the recombination. Usually people say the peak of the optical is the point where recombination starts. No, it's not. It's a point where the temperature drops to roughly 9,000 degrees, or 10,000 degrees. This is because this is where the optical is. R-band, for example. Okay, so it's not far. Wait a few days, maybe a week, recombination will start. But the peak is not related to recombination. And I will skip that, I will skip that, and I will skip that. I would just want to show 3 or 4 more slides, but from a different, yes, this one. The last thing, I want to tie everything together and to show you something. Maybe I will be able to do that, yes. And to show why we get this diversity. So we learned about cooling emission, radioactive contribution, and we saw that we have both. And we actually have both in every supernovae. So what is defining what we are going to see? Are we going a cooling emission dominated supernovae like type 2Ps, or radioactive dominated like a type 1? So this is a bolometric luminosity going up very quickly, shock breakout, 10 to the 45 ergs, down very quickly, and then doing that. If we look at the nickel luminosity, and by the way, here, how bright it's going to be here, you saw, this depends on the radius. Also somewhat on the mass and somewhat on the energy, but mostly on the radius. And the duration here, depending strongly on the mass. Much more mass, it will be later. Also depending on the energy. This is the radioactive heating. The time of the peak depends on what? On the mass. So the time of the peak of the radioactive heating and the end of the plateau here are at the same time. Both of them depending exactly on the diffusion time scale, the same diffusion time scale. So this peak is at the same time. But the height of the nickel depends on what? How much nickel I have. So the ratio actually to the zeroth order or to the -1 order to the -5 order, depending on how inaccurate you want to be, you have two separate contributions. One is coming from the nickel, one is coming from the cooling. You just add them up. You see, they give you what you see. And this would be true if the opacity will not depend on anything. The opacity would have been constant, then you can use that exactly. The opacity is not constant, so you cannot. So if we go to the R band, I remind you, the R band, you do not see this nice decay here. It's rising. But it will rise to some level, much faster than that. And this will rise to another. So the question of whether you see a cooling envelope or nickel depends on some relation between the radius of the progenitor and the nickel mass. Both cases, you have the same energy of explosion, the same mass. It's one explosion. If you have less than 0.1 solar mass of nickel, radius larger than 500 solar radii, roughly, the cooling emission will be brighter. You will not see it. Sorry, you will not see the nickel. Up until when? Up to here. And this will give you roughly type 2p. If you have a lot of nickel, or 0.1 solar mass of nickel, and much smaller progenitor, let's say like 87A, then the optical will go up. At first, it will go up by the cooling emission. We'll have here some phase of cooling emission. Short phase. It will be brighter than the nickel, but this will be very short. And then the nickel will kick in. The cooling phase we can always see at early time. If we would be able to see at early time, especially if we can look at the UV. But very quickly, it's becoming fainter than the nickel, and we get an 87-like. Okay, and this is what giving us, just play with the radius and the amount of nickel, and you get not everything, but to a large extent, the variety of things that you see here. How much time do I still have? Or I can stop here. No, really. Okay.
Thank you very much.
Do double-peak supernovae fit into this picture?
So let's continue. So now we can compose. It will take me 5 minutes. But he asked. And I didn't ask you to ask before. So now we can use everything that we learned so far to ask, okay, so what are the hell double-peak supernovae? So usually supernovae look like this or look like that. But every once in a while, instead of saying hump, a one hump camel, we see double hump camel. Okay? So where is this double hump camel coming from?
Not in Israel.
Not in Israel, but in China you can. In Israel you also see a single hump. In some cases we see something like that. This is in V band, going up, going down, going up, going down. This is in the R band. Okay? And this part here is exactly what you would expect from a nickel-powered supernovae. So we know the second part is powered by nickel. But what can be this part? Now, I showed you before that the time over which we get the peak from the cooling and the time that you get the peak from the nickel is the same time. So how can it be that we have the same time for both, but we have, if you want to explain this, for example, by cooling emission, how can it be cooling emission? Because the time here is much shorter than here. The answer here that one solution for that is to build a progenitor which is slightly different. This is the original progenitor. In the original progenitor, both the time for that, for the nickel, and the time for the cooling emission came from where most of the mass is, and most of the mass was roughly where near the edge of the star. So most of the mass was here, maybe half star radii, something like that. But if you compose a different star, where we have most of the mass inside, say 10 to the 11 centimeter. And then put here some extended envelope. Extend it up to 10 to the 13, but put here much lower amount of mass. So all my nickel is here, but all my cooling emission will come from that. Because here the radius is huge, so this is contributing to the luminosity. And I remind you, remember that the luminosity didn't depend on the amount of mass, just on the velocity and the radius. So the velocity here is uniform. This will dominate. And then we get that. This is what we get for the cooling emission. Bright peak, but very short in time because the mass is low. And then you have the second contribution from that, which is much fainter and longer. And here the nickel kicks in. So you get the double peak. And everything that we calculated before, you can apply here. Use the nickel story for the nickel, use the cooling emission for the extended envelope, and you can constrain the properties of this and the properties of that, and everything. Did it answer? Okay. Oh, no. Nobody knows what is the origin of different slope in type 2Ps. There are several stories. I didn't find any one of them extremely convincing. Maybe they are correct, but there is no conclusive evidence. It has something to do with a combination of the mass of the envelope, the structure of the envelope, the composition of the envelope, and the amount of nickel. And that's it.
Wait, let's start with that the fact that it is a plateau is sort of a coincidence already.
Yes, this is true. This is true. It shouldn't be, a plateau is not something that you would predict a priori. You can get a story where a combination will give you actually a rising light curve. You can get certainly a story where it's giving you a declining light curve, you see it. Okay? Now, at late times, nickel starts contributing. Although it's subdominant, it starts contributing. Actually, what nickel is doing to type 2Ps is two things. It's extending the plateau, and it's extending the plateau in two ways. One way, it's making the combination slower. So this extends the plateau. And the second is also flattening the plateau because it's contributing some energy, not only affecting the recombination. Okay? And third, it's extending the plateau because it's giving you energy to radiate. So it's a combination of all of them. My guess, and this is my guess, it's not only a guess, it's an educated guess. Part of the story is nickel. Certainly not all of the story. Part of the story is nickel. You have more nickel, you have flatter supernovae. The second part, this is my guess, is mostly the structure of the envelope. Mostly the structure of the envelope. Play with the structure of the envelope and you will get the answer. This is my guess. I didn't prove it. My feeling.
I think for the double peak picture, probably you can also get not only the single exposure, maybe our first peak power by nickel of the envelope cooling, but then maybe later you have a second stage interaction, then you have another.
Actually, for the second peak, it's easier to know what it is. So at least if you see, if this part is 1 magnitude per 100 days, then this is nickel. Okay? So this is easier. If it would have been interaction, you have the very strong indications for interaction in the spectrum. So you can see. For the first peak, it's more difficult. The first peak, you can say, okay, I had some engine working in. For the first peak, you can start playing some games. So this is certainly not the only solution. Okay? But in some cases, we know it's correct because if we have a pre-explosion image, we know what is the radius. And if the radius is several times 10 to the 13 centimeter, and we didn't see any cooling emission here, then we don't have a lot of mass. So we must have from here we can measure the total amount of mass. So there are cases where we saw the progenitor before, we know the radius, it was a yellow supergiant, and we saw these two peaks. So the first peak is coming from low mass extended envelope.
So there's also maybe possibility for giving a hydrodynamical instability to mix out the nickel to early on to power such kind of first peak.
No, you cannot do that. You need a huge amount of nickel. See, from here you can measure how much nickel you have there. So I think that here you should have more nickel than mass. You estimate the mass by the duration and everything? No, you cannot do that. It can give you some small hump like plan was showing. But no, something like that.
Yeah.
The very rapid growth before before breakout that you showed on one of the slides.
This was a bolometric luminosity.
Yes. So
That's
the very
yes.
So is this the slab that you showed with the drawing? Is this the time scale that it is going?
No, this is a time scale for diffusion through the breakout layer. It's very, very short. If you look, for example, at red supergiant, it will be 100 seconds. This rise time will take 100 seconds. If you go to a more compact progenitors, it will be much lower, much shorter than that. So this is a very rapid. This is happening on a very short scale, 100 seconds or so, and most of it is going in wavelengths that we cannot see. The temperature is 100,000 of degrees, at least. This can be more if it's out of thermal equilibrium. Also in the optical, we'll see a rise on this time scale.
You have here that the duration of the plateau depends on the percentage of mass, but almost all TPs have a plateau duration of like 100 days. Exactly. So
No, it's not exactly, and this is a big question. And up to a factor of 2 or 3. No, but this is what I did here. I did here a calculation, which is accurate to a factor of 2. You cannot, anything that I said here, you cannot take home and say, now I measure to an accuracy of 20% and apply what I saw here, and I can tell you that the mass is. Okay? I did an order of magnitude calculation. It gives me an order of magnitude result. It's a big, first of all, not all the plateaus are really 100 days. When you start looking deeper into the data, you see that it's not entirely correct. The range of masses is not very large. What is the range of masses? Factor of 1.5 usually, more or less. You start exploding them at 10 solar masses, and if they have more than 15 solar masses to begin with, they lose everything they had before to winds. So the range of masses is not huge. You affect by nickel. You affect by recombination.
If I understood correctly, is the relative brightness proportional to the amount of nickel produced in the explosion?
Yes. No. When I say I was laughing and saying yes, because this is something to do with the explosion mechanisms we don't understand. It shouldn't be like that. There is no reason whatsoever. Just from the light curve, I can can produce the same amount of plateau with 0 amount of nickel. There is no.
The first part of the talk, right? Producing a plateau basically with no nickel.
Somehow there is a conspiracy which has something to do with the explosion mechanism, which is a hint to people that try to explode stars, where there is a tight correlation between the brightness of the plateau and the amount of nickel which is produced. So there is one observationally. Theoretically, I cannot tell you what is the origin. And certainly the light curve doesn't require that.
Well, you can say it's explosion energy.
Okay, you can go with that, but it's not clear why explosion energy give you both.
I understand, but
Yes, okay, if you want to type, no, it also may have something to do with the core mass, which is also related to the explosion energy. So yes, but basically it's true, more energetic supernovae giving you brighter plateaus and more nickel mass. So you can go one step inner. You can go next step. Now you should ask the question why the energy is giving you why is it related like that? Yes,
Okay,
but this is true.
Saying